Well, welcome to eBPF, Revolutionizing Observability and Telemetry for Modern Applications, which is a mouthful. This is about eBPF and how it relates to observability. Just a quick overview of what we're going to be talking about today. We're going to quickly cover the just observability landscape, where we are with observing modern applications, go into eBPF and some of the technical concepts that make it really good for observability, then kind of tie those together into what these mean together, and then just look a little bit at what the future of eBPF and observability could be and kind of wrap up with some questions.
Show of hands, who's heard of eBPF? Who's worked with it? Couple? Okay.
Cool.
And everyone's heard of Telemetry, right? We'll be talking about that as well. Okay, awesome.
Awesome. Yeah, so this would be, for some of you, this might be a little bit of review. Some of you, it'll be a good introduction, but I think it's a good, mid-level slide for a lot of people. So this is us. You want to introduce yourself?
Yeah, hey folks, Eric Horsman, VP Solutions Engineering. I've been in the observability and in the tracing game for a long time. We'll talk a little bit about how eBPF plays into that. Dynatrace, Turbonomic, and Precise before that. Working with lots of the companies out there. And yeah, hockey's my life outside of this. I have two boys who play hockey, so in it quite a bit.
And my name is Mike Dame. I'm a senior software engineer here at Otigos. I've been an OpenTelemetry maintainer, Kubernetes maintainer, Red Hat and Google. Now I'm working at Otigos, where we do eBPF-based application tracing. And I'm a big NASCAR fan, and I will be at Loudon this weekend if anyone else will be there. So with Eric's experience, he's going to kind of talk about the landscape.
Yeah, no, absolutely. So for a long time for APM, there's metrics, there's logs. And then there's tracing. So essentially, from a tracing perspective, how you're typically getting that data is doing some level of instrumentation, right? So oftentimes it's manual instrumentation of code, sending it to some sort of platform, storage facility, data lake, and then displaying it on one of the common tools out there. I'm sure a lot of us use Grafana and HyperDX and other products as well. Next. And how you do that really hasn't changed. You either do it manually, or if the facility exists, like it does in Java, you do automated instrumentation, and this is bytecode instrumentation with Java in the runtime. So you can either do it before you compile the code, or you can actually do that after you compile the code, right? Is some jar that uses a set of libraries that you're going to instrument by default. So let's talk a little bit about how that works, and we can then talk about how it's different when you're utilizing eBPF. Manual code's pretty straightforward. Your code will actually send out its instrumentation to some sort of collective facility directly. It knows how to do that, hooking into that collection facility, and then that goes directly out to a repository. With bytecode instrumentation, you're actually modifying the code itself. I got a pointer, so I'll use that versus my hand. How's that? Better, right? Even better for the camera too. Yeah. So we actually modify it as that gets injected, and what happens is there's all this work that's also done within your application server before it actually sends it out to the APM collector. This is how all the bytecode instrumentation products work. This is how auto instrumentation with OpenTelemetry works as well. Before it goes to the assembly or to eBPF or anything else, you're doing all this work inside the actual application server itself. So some trade-offs to that is, particularly auto instrumentation, is its partial language support. So you need someone to build that instrumentation list, that framework set, to actually do that instrumentation itself. And it's really different from every language. I think in auto instrumentation for Java, there's over 300 frameworks supported, right? And you go to Go, and there's probably 10 to 12, right? So there's not really that many that are supported out there. There's obviously a lot more Java as well. You can't do compile languages until Go, but C, Rust, there's no auto instrumentation. So that's manual instrumentation, which you either have to write yourself, or you maybe can run something to go against your source code itself. And obviously that you have that manual. So anywhere where there's gaps, there's not frameworks for auto instrumentation. Even in non-compiled languages, there's a lot of custom coding that you have to do, which is very intensive. And still you're paying that performance penalty of running all that stuff within your application server. In addition to that, it can lead to stability issues. So if people make changes in OTel for Python, we've seen quite a bit, in fact, it can crash your application, right? You can have conflicts.
You're inheriting any bug that's in the observability is now your bug too,
Yep.
because it's embedded into your code.
And we see that all the time with customers, right? So we're fixing a lot of those frameworks that are out there and existing today and supporting it for our customers. And then in addition, the slow startup times. We know a lot of folks that can't do instrumentation and things that have to start up fast. Lambda can be a big issue because there's a lot of instrumentation uptime trying to actually start that up so people can actually use your application itself. So the thing is we feel like it's getting worse as well, right? You have things like Lambda, you have very ephemeral types of applications. You have a lot more services, microservices that have to be instrumented in a lot of different languages. There's an emergence of things like Go and Rust, which are compiled languages. So I think what you're seeing is there's more and more chance that you're not going to be able to instrument these things to actually see that data, see that telemetry, see that tracing. So just to kind of hit eBPF, to introduce it at first, is we actually already see it transforming a number of places. So you have things like Cilium and Catran and Calico on the network side. On the security side, and also we see a lot actually now with profiling as well, right? So eBPF profiling. But until now, there really hasn't been a lot in the actual tracing, the actual distributed trace field itself.
And yeah, I think that kind of leads into talking about the technical stuff that enables eBPF for tracing and what kind of differentiates tracing as a signal from metrics and logs and the other observability signals. So kind of going to go over some of those technical details of eBPF. Three big things that I want to hit on. First is eBPF is portable and it's secure, which is very important for observability. You got to make sure what you're watching, but you also want to be able to observe everything as much as you can at once. It can dynamically attach the ability to start observing, stop observing without having to recompile or restart your applications. And it also supports built-in persistent data structures, which especially for stuff like traces or metrics, you need to be able to keep track of what's been changing and how long it's been changing for. Otherwise, you're just basically looking at data points individually. So eBPF itself, kind of taking a step back, eBPF is not a niche project. If you've never heard of it or you're just starting to hear about it, it's not something I need to look up like how do I download and install eBPF. It's native to the Linux kernel. It's an actual kernel project. And it's actually in use in a lot of places. At Facebook, every single packet that's gone to Facebook since 2017 has gone through an eBPF program. So you're actually, if you have a Facebook, you're already using eBPF without even realizing it. It's secure and it's portable because eBPF by design is built to run on every Linux kernel. It's built to be cross-version compatible in Linux kernels, and it runs in a secure sandbox. And the code is verified before it's loaded into that sandbox. So you write an eBPF program, it can't just do anything. It's got to run in this safe sandbox that is contained on the host. As far as observability, eBPF really hits the two top priorities that I've seen in my career with observability is that overhead. So you can minimize the amount of stuff that's hitting your business logic and taking consumption away from what's running in your application, kind of offload that. And the investment, which is the time, and time is money. You don't have to spend as much time going to every single application, writing trace code, recompiling, redeploying it. And the new thing that's unlocking that Eric really hinted at is the ability to get into compiled languages and really do this deep tracing into the application layer itself. So the first point that I wanted to hit on is the different attach points that eBPF has, and these are my two favorites that I like to talk about. There's a couple different ways that you can attach. You can also attach to network, devices. You could sit on a port, and every time a packet comes through, you can run a program. But with the way that these attach points work is that the kernel knows when this certain function is called, run this eBPF program. So in this case, I'm talking about two different types of attach points called kprobes and uprobes. And I like to start with kprobes because that kind of builds to what a uprobe is. A kprobe is talking about if you've got a kernel function, such as a syscall, the kernel can know every time that syscall is called, such as a file is opened or a program is started, go and run this program. So that kind of makes sense, right? Now you can do the same thing in a compiled user application. Every time this function is called, go switch to the kernel quick, run a program, pass it all the context I have about that function. So all the arguments, all the return values at the end of the function. So you know everything that went in and came out of the function because you're attached to that spot in memory. And so that last point provides the application level observability without needing to recompile or restart, because this is dynamic. Just like you can attach to a kernel point while the system is running without having to recompile your whole kernel, you can attach to a user space point without having to recompile or restart your program.
Hey, Mike, like to that point, you're talking about doing a lot of things in the kernel. Sounds really scary. Tell me a little bit about the security of this, and other issues that it could cause.
You're supposed to be giving this talk with me. But yeah, eBPF, that's built into eBPF, that sandbox that I mentioned. When you load code into eBPF, first every instruction is analyzed to make sure that, one, you're not doing things like infinite loops or accessing memory that you're not supposed to be accessing. I mean, this is all vetted by the Linux maintainers. They don't put functions into eBPF that aren't safe, or else it wouldn't be in the Linux kernel. Like, Linus wouldn't allow that, right? Same idea here is that it's running in that sandbox and it doesn't have the access to do things that it shouldn't be able to do. So it's safe by design, really.
Yeah, and we do this in some of the largest financial companies and retail companies in the world that are super secure. So absolutely safe. Go ahead.
The next point, so you've got the dynamic attach points. That's where you've hooked in, and now you're able to see what's going on. When you get to observability, you need to persist that data somewhere, and eBPF provides a couple different data structures. Two of the key ones that we use are maps and ring buffers. And a map is just what it sounds like. It can be a hash map. It can be broken down per CPU based on whatever you need. The main idea is that you have a key, and you can store arbitrary data in that key, and you can look it up. What that gives you is the ability to save data, to update data, and these can be shared between eBPF programs, not just in the life cycle of one eBPF program. So now you've got programs that can talk to each other, programs that can run, exit, and then pick their state back up later. And then the same idea kind of with ring buffers, where when that data is done, you can push an event into this ring, and then something else can pop those events off and read from them, either in the kernel or in the user space, which we'll kind of get to. And these live outside of the eBPF code. Everything doesn't have to run in memory. It's actually pinned into a virtual file system on your device. So these together kind of create without these, observability would be much tougher with eBPF because it makes it persistent.
Just any questions out there right there? I want to pause. We're going to take questions at the end too, but you look like you had a question in the middle. So yeah, absolutely. Well, I'll repeat it for the mic as well. Actually, no, you can just say it into the mic here.
Does this work for containers, OpenShift?
Yes, actually, that's how Odaghost runs, mainly on containers, and we do have an OpenShift version too, which has its own requirements. Working with SE Linux, making sure that these files are accessible and that you have the right permissions. But yes, absolutely, it's kind of the same idea, just with that other layer of going into the container itself and down to the host. So all the containers are sharing a kernel on the same host. So if you're loading an eBPF program into the host, all those containers can be read from and accessed and write back to and share the same eBPF program. And that's how you get a lot of efficiency from observability, because for example, you don't need a sidecar container for every container to observe. You can load one program into the host, and now it can observe all of your containers securely.
Yeah, really anything that runs on Linux, right? So Kubernetes, Docker works great.
Yeah, I guess opening with this works on Kubernetes would have been a good start, because that's really our main thing. We do it for VMs too.
Yep.
But it's Kubernetes and OpenShift is our big approach. And then finally, these programs have to be compiled and they have to be loaded into the program. So how does this all come together? This just kind of I know when people are explaining this technical stuff to me, I'm like, how does it become a thing? eBPF programs are compiled just like other code. They get compiled down to bytecode. There are special compilers for eBPF. You can write these programs in C. You can write them in Rust. I think there's some Python libraries for it. I think C and Rust are the main ones. We do mostly C. But then it has to be loaded into the kernel, which you use a tool or a library to do that. It's basically like deploying your container or deploying your application, but you're doing it telling the host, deploy this program. When it's loaded into the kernel, the eBPF verifier does that step of checking all of the instructions, making sure there's no loops, no out-of-memory access, no potential nil pointer dereferences or bad loops that could go beyond their limits. But this, in practice, this becomes a lot to do manually. So the same ideas that you have with deploying a container or with deploying a VM, the kind of DevOps approach starts to come up, and you need tools to orchestrate this for you. So that's where these tools become their own big projects. Things like Odagos or like Cilium. Not to compare us to Cilium, but there's a lot that's going on to manage, load, unload, attach, make sure this is all happening fast and usable. And so that's where you start to get what's usually referred to as the user space eBPF program. So you'll hear that a lot, where you've got the kernel space eBPF program and the user space eBPF program. And so these will be talking. When I talked about that perf event buffer, that ring buffer, when your eBPF program is firing off these events, it's got a trace that it started and stopped, and then it fires it into that perf buffer. Now from user space, you can read from that and do code just like you normally would. Your logic of reading, oh, this was the event, this was the time, I'm going to format it into this data structure. That's exactly how we create traces. We format them into OTel format and then export them off to the collector in user space. That's been running as a second asynchronous process from your user application. User application was only traced for a very, very much smaller fraction of a time than would be manually. Popped off, sent to this asynchronous user space program. This is an example of what a small eBPF program looks like. So it's kind of small up there, but it's kind of small in real life too, because like I said, these programs are verified so that there's a certain number of instructions maximum that you can have in these programs. So I like showing this because it kind of shows the accessibility of eBPF. Like anyone can really feel like a kernel developer when you're writing eBPF code and see like, I'm not a C programmer, and I consider myself one because I'm doing this stuff all day. But these programs are very small. They're required to be small. They're easy to approach. A lot of them are really like one file. You can chain functions together. You can chain programs together. But this example here, since it's small, I can just kind of show you're creating one of those maps up top. That's the struct that's happening here. And then every time, this is linked to the exec-v syscall, which it runs whenever a program opens. So basically, what this function would do, what this program would do, is every time a function opens on the host, it'll increase a counter in a map. And then you could go read that map from a user space program and just get a count of this is how many times functions have opened on the host. You can do all that with here, and it runs for every program that's opened on the host. So this is the flow of a request, kind of putting that all together. If you were to think, like, what does this look like in practice? When you've got your eBPF programs loaded into the kernel, so the kernel space is kind of between this dividing line here, and the user space is above the dividing line. You've got your user program triggered by user functions. It's going to be, say, the application that you're observing. And the section on the right, the eBPF loader, is what I said is going to be popping off of those maps. That's that user space eBPF application. So the loader will handle inserting the code down to the eBPF verifier. And when that's all verified, it'll load it into the kernel. And so each time that user space function happens, the loaded eBPF program very quickly gets that context of the function, reads the arguments. That could be in Go, it's usually like the context argument itself, where you've got your headers, request headers, whatever you're looking for. But it could be other things too, such as the function name, usernames that you've inserted, query paths, query arguments. It can be writing that data down to the eBPF map that persists out there. So for very quickly, it sends that data to eBPF, returns. It's running saved in the eBPF map. And then that data keeps getting offloaded to the eBPF reader in that user space application. So all the pipeline processing of, open telemetry can be very memory intensive of running in your application. So shift that asynchronously off somewhere else so that your business logic can continue to run without having your observability bogging it down.
Yeah, and so right here is that line, and this is actually where encryption happens too. So if your programs are encrypted, you're not able to get that detail if you get up below this line. This is really what we call that network layer, that syscall layer. That's really where most of the eBPF programs to date got their data. This eBPF place is like a brand new location where you can actually get distributed tracing, as Mike said, that deep, detailed data before anything gets encrypted as well, which is pretty interesting.
Yeah, that's actually a really good point that I think that we could have hit a little bit more on, is that a lot of these eBPF programs, we talked about it for security and networking and even observability too. When you're running at the kernel layer, like security makes sense. You're blocking functions that run. Networking it's very good for building out service maps, getting metrics about things that are talking to each other or ports that are hitting data. But then once you get into things like traces or wanting to get that application layer observability, if the requests are encrypted up there, you can't read it at the network layer because encryption happens in user space. So you need to peek into that with eBPF lets you do that into the user space.
Yeah. So and what that does is really let you transform what you're doing and taking all of this work out of the application server. Now your application can just run and now sends it to that eBPF code. And this is actually where you can actually do that instrumentation itself. And now all this work of compressing, encrypting, molding that data, looking at the actual libraries in which you're going to instrument are now is actually done in system memory versus your application itself. So and this is really more of a runtime application, but it works the same way in compiled. Everything is outside of your process. So it's really actually just looking in, doing that instrumentation. And now you can send that telemetry out to, if its output is open telemetry, you can now send that telemetry to an open telemetry collector and off to your observability platform of choice.
And I like this slide because it kind of ties back to that hybrid or that bytecode instrumentation. You can really combine the bytecode auto instrumentation with eBPF too, which is what we do in some applications.
Yeah, most of our customers already have instrumentation, right? So you can do that combo.
So there's a lot of benefits to a little bit of best of both worlds that you can do with eBPF if you want. But yeah, the biggest benefit besides not having to write code is minimizing the overhead, like we've been talking about a lot, that process overhead. What it really comes down to is that if you're writing code and inserting open telemetry pipelines or any observability pipelines into your application, that's consuming resources from your application. You get kind of a Heisenberg problem where what you're observing is now different because you're observing it. So shifting as much of that as you can asynchronously out into something else gives you better observability. You've got all these, APM tools that are talking about, we've got the best graphs and the best visualization and AI, agents that can tell you what's happening. But if the data going into it is, tainted by being observed itself, it's just not going to be as good. So that's what eBPF provides, is that path to shift that overhead to that asynchronous pipeline, with the caveat that each of those context switches come with overhead. So you have to manage that. You have to know what you're doing because there's no free lunch, right? You have to make sure that you're doing this appropriately. But if you do it all correctly, what you get is now not only is your overhead of your observability minimized, you've centralized it into one place. Pushing out config changes to your observability can happen by just updating one eBPF program, which can then dynamically go back into your application and update there. So instead of, like in the first slides, we were talking about that the auto instrumentation that's available is different for every language. You've got Java agents, you've got monkey patching in Python, and if you wanted to roll out a change into all of these, you need to make changes to how all of those are deployed. But if it's just an eBPF program, you go to one place. You can make sure everything's standardized. If you've got 12, 20 different microservices of all different teams owning them, and you want to say, we're switching this attribute now, the company is changing its name, update your attribute, you've got to get every one of those teams and every one of those languages to update their attribute and hope that they spell it right. Otherwise, your traces are all going to look different. So this is where the DevOpsy part of eBPF really starts to hit home in those programs like Cilium, Otigos. The management at the high level is super important.
Yeah, and so Mike was talking a bit about performance, and this is kind of what we've seen, and we've seen this time and time again with multiple languages, is with zero instrumentation, and then with eBPF. So very little overhead. So that means not only is it lower overhead for latency sensitive applications, but I can instrument a whole lot more, right? So I can add more high cardinality data. I can get more arguments and message payloads and query values in addition to that as well. So huge benefits from a performance perspective. If you have a high latency application, if you wish you could get more payload data, but it costs too much from a performance perspective to actually collect that telemetry.
And this is backing it up with a little bit better graph. I didn't like the little drawings. This is from our site. This is
I like the drawings.
Yeah, this is the actual graph that we did, and the kind of details to back it up that show pretty much exactly where that big orange line that shoots up in latency, that's manual instrumentation. So when you start to hit that, it looks like it's about 99th percentile. That's where the difference really starts to show. And the table on the right is showing just how much you will hit the 99th percentile. If that sounds like something that's uncommon, it's actually very common. Our 50th percentile hits the 99th sometimes on some things that I'm running. All comes down to context propagation. We don't have a lot of time to talk left, but the main takeaway is, like I was saying, those function arguments that you get is that you can add the business context into what you're tracing and pass it on to the next application very easily. This is just a main tracing concept itself.
Yeah. So what's that mean, right? So right now we're just on the cusp of introducing this code level instrumentation to get that deep tracing. We've done it for a few years. There's some folks starting to do that, but really what this means is even things like custom methods and custom instrumentation. Not only can you instrument your custom code without doing it manually on the fly, but you can actually do it without even restarting your application, right? So you could actually instrument on the fly itself. More compiled languages. So Otigos today has done C as well as Go, but you can actually do any language that's out there. Things like Erlang and Rust we talked about with someone earlier as well. Think about it from a legacy perspective too. You have an application in your system that maybe the folks aren't around anymore. Maybe it was a consultant that built that app. Maybe it's a piece that hasn't been touched in 10 years. And maybe you containerize that. Maybe it's on a Linux machine. But I've never really been able to get telemetry outside of logs. Now you can actually do that instrumentation and do that instrumentation on the fly. And then that kind of leads into some more things, and I'll touch on a little bit, and then you can kind of expand this point a little bit, is if you think about eBPF, there's also the ability to do eBPF profiling. So with eBPF profiling and instrumentation, you can actually automate that whole process eventually in the future, where you just say, learn my app, see what you want to instrument, learn those branches, and give me that telemetry.
And I think the biggest thing that the acronym that everyone's looking for is AI, which stands for autonomous instrumentation. Laugh now. But I had to mention something about it. But really, what AI unlocks for this, eBPF kind of enables AI to feed back into these applications with all of the dynamic ability of eBPF and the host level centralized ability for it to feed back. Your AI could be seeing where errors are coming from, dynamically deciding, okay, we need to increase the observability here, and then turn it back down once the error goes away. So it can feed back into itself, it can learn from itself, and eBPF is the tool that enables that. And even besides what AI could do with eBPF, eBPF is also working to enable AI. I'm working with some of the LLMD contributors. We have some here to bring some eBPF observability into LLMD, because obviously the overhead is huge there, so you want to minimize that. But that's just some ideas. These are some of the resources from this talk. This is the intro to eBPF. These are some of our repos that we have in OpenTelemetry that are doing eBPF-based instrumentation. I love the Learning eBPF book by Liz Rice. It's a great resource. And finally, I gave a talk last year with Tyler from Splunk, where we talked about this a little bit more in depth with how it works specifically with Go and that Go instrumentation project up there. So if you liked this talk, it's a very good intro to that talk. I would go check it out.
I just wanted to thank everyone and open it up for any questions. I know we're right at, oh, look at, perfect, thank you. Got queued up for Q&A right on time. So any questions by anyone? Yeah, you could, yeah, go ahead. Yeah, actually, let me bring this around. You want him to answer, not me, anyway.
Okay. Yeah, hi, Mike. Thanks for the great presentations. I wonder, do we need to escalating the privilege in order to run the eBPF program?
Yeah, and that's one of the cool things about eBPF is that the different functionalities that it has can be broken down into different privileges. So if you're loading an eBPF network program, you can just grant I think it's like sys network admin. There's sys like cap sysadmin. All those different capabilities that you're familiar with, eBPF has really been kind of modularized into exactly what you're doing. You can give it exactly the permission that you need. And so you get that along with the program itself is running in a safe sandbox.
Okay, so question number 2. So how the eBPF can be integrated with the Open Telemetry or any other, let's say Grafana or Prometheus, something like that?
Yeah, I mean, eBPF is kind of the gateway, the tool to get the data, because all Open Telemetry is a format to structure that data. It's data about your application, the information, the context, the business context of what is being traced. So eBPF unlocks that by being able to look into your application dynamically. It's really the tool to just open up the application, lift the hood, see what's running, and then once it gathers it all, you can spit it out into, like I said, your user space application, and that will format it, package it into just the OTLP, basically JSON standard, and then anything that accepts OTLP, Grafana, you got your Datadogs, Google Cloud, all of these. So it's eBPF. A lot of people ask that, like, how does eBPF compare to Grafana or these backends? And eBPF really isn't the backend. It's the tool to get the data to send to the backend. Thanks.
Hi. So my question is one about security. In a cloud environment where you might have a multi-tenant host, if you're trying to capture telemetry via eBPF programs, those necessarily need to be executed with privileges, and they run in the kernel. Therefore, they're not really namespaced like a container would be, or even a VM. So is there any mechanisms that you're aware of? Is it a concern that eBPF programs collecting telemetry for a specific client application might be able to observe other applications that they're not supposed to be able to, other tenants on that host?
Well, yeah, I mean, there's ways to kind of get. I mean, obviously, first off, eBPF is built, like I said, with that design to be safe. But even in the user space, like with Otigos, we have our user space program allows you to select which applications you want to instrument. So you can say, I only want to listen to or instrument these certain applications and attach to these points in memory. So the first layer is up in the user space of where you're loading the programs, of get what you're looking for from there. And then you can rely on the built-in security barriers that eBPF has built into the kernel itself to prevent any bad actors that gain that access to get out.
So from a beginner's perspective, somebody who's just kind of getting started with this, is there anything that we should keep in mind that it might not be good for? Or from the perspective of someone who is just used to logging their application, are there things that you have to keep in mind when you're trying to transition to something like this?
Yeah, that's a really good question. I mean, I would definitely keep in mind, some things that you can run into, and eBPF will bonk you on the head if you try to do it wrong. Is, like I mentioned, those instruction limitations. There's memory limitations to what you can do. You really have to kind of think like a kernel, like a low-level embedded developer of what you're going to do. You can't just throw anything into it, and you really have to keep in mind, how much data am I tracking? How much am I putting into a map? How much am I loading into memory? Or eBPF will say, no, your data structure is too big. you've got too many instructions in this program. You got to break it up a little bit. So it kind of helps make you a little bit of a better programmer too, because it keeps you on your toes that way.
Hi. So could eBPF also be used for, let's say, Android OS or anything that's hardware, like for a headset or for a device like a phone?
That's a really good question. Yeah, I don't see why not.
It is, yes.
It is.
We've touched that yet, but
Yeah.
you can get eBPF there. So I don't think anyone's done it quite that.
Yeah, I've never been much of a mobile developer, but it's the same idea. It's running basically Linux, so you can offload off of your user space applications into that kind of embedded system.
And you can say this in the mic so they can hear us, but it's something that we do want to look at in the future.
Yeah, Eric says it's something that we do want to look at in the future.
Anyone else? Question? Pass it down.
So this will be the last one.
So what can Otigos do with eBPF that is different from, say, Grafana Bela?
Yeah, so we're actually good friends with some of the people at Grafana Bela, and they donated the OB project, which is built off of a lot of the same stuff that we use. I think what we do a little bit better right now is our application layer observability. It's shared a lot between what they do. Bela has been really focused on metrics, and they do that really well. And I think what we're able to do is the internals of the libraries themselves, and what we've been working with different customers to pull out, customize different libraries for them. Plus, we're a little bit more of a control plane, and Bela is a very good agent. So I think that, like I was talking about, how you can choose the different applications to run. We have different RBAC controls and everything. Yeah, they're both very good projects, and we're good friends with Nicola and Raphael and those people over there. So
Yeah,
check them out
I think
too.
it's a concentration on deep tracing and details versus metrics, right? Is really the big difference from those that you'll see today. So absolutely, both eBPF and in the same family. We have to wrap up here. Thank you very much. If anyone has any other questions,
And we're hiring too, so check us out if you want a job.